Hello, everyone. Thank you for choosing to join us for this first ever vector search conference. And I think this is a truly exciting market. There is a lot going on here, and I hope you will learn a lot from this day ahead of us. Now, what is interesting for me is this market of vector search databases, or vector databases as they're sometimes called, has been developing very rapidly. Well, at least if you think about the database space, because databases are rather conservative and move rather slow. Just 5 years ago, there was almost no vector search databases, and now vector search became a key feature for relational and non-relational databases alike. At the same time, we still see a lot development going on. We have a feature set which is still being developed. We're still figuring out what features developers or actually AI agents need in AI apps. And also what is interesting from a business standpoint, what we see, what AI enablement is really the key driver in a evaluation for those databases. That was, for example, a key factor in recent acquisitions for companies like Neon and Crunchy Data, which were recently acquired. Now, let's talk about vector search specifically. What does this feature set in a database provide? Well, actually a lot. A lot of features such as movie recommendation, product recommendation, right, or some sort of search called semantic search really uses this vector search functionality underneath. Now, as I mentioned, vector search can be used for a lot of stuff. In this presentation, though, I will pay a specific feature, a specific focus on the search functionality, which is something I just happen to spend the most time with. But I think it's worth to note what the vector search, while they have a search here, is not really only used to build the semantic search applications. It's actually used for much more than that. Let me show you this slide. This shows their year in which vector search functionality was added in the notable databases. And you can see here indeed what the first databases started to implement this functionality in 2019, right? And then we had the explosion in 21, 22, 23, right, where a lot of databases got those features added. I would also want to point out the notable exception, and I would say unfortunate exception, which is MySQL, which only have a vector search functionality in a proprietary version, though there are some third-party implementations as well. I think that is an extremely poor and hostile to the MySQL development community decision from the Oracle side. Now, I mentioned that vector search is important, but I wanted to give you a couple of highlights. It is interesting if you look at Elasticsearch, for example, they are choosing to highlight the vector search as a key feature in their GitHub. Well, it's even higher than a full text search, right? It's so known for. And on a website, they are promoting that as a world's most downloaded vector search database. Enterprise DB, the well-known PostgreSQL company, or EDB, which is their new name, are also very much pushing as PostgreSQL AI, which changed from their developer focus a few years ago. And of course, MongoDB is also does a lot of investments in building AI compatibility. Now, you may know, though, is what AI and machine learning is not new, right? And actually, we use that in applications for many years, right? Even decades. Why is all this attention? And I think that has a lot to do with their new kind of AI which appeared recently, the generative AI. This will be your generating images, videos, right, or chat with ChatGPT and alike, right? And I think that just was mind blowing for so many people. Now, everybody, not just technologists, could understand AI, and it was kind of magical for many people, right? It was very hard to believe what those texts or images could actually be created by AI and machines and not, humans, writers and writers. And that is still really the thing which is impacting the industry a lot, right? I think we still didn't quite recognize what this huge change in the AI capability is going to bring to the market. But let's move on from that and talk about more low-level things. Let's talk about the vectors. As we talk about vector search, we of course should talk about vectors. Now, you may wonder, we are talking about AI and generating wonderful poems or images. What does a vector have to do with all of this? Well, in reality, if you think all their AI and machine learning the systems is really a lot of math underneath them, and really more specifically vector and matrix math, right? So that is why if you use a technical term, we are talking about various forms of operations with vectors. Now, when you talk about some real-world objects, you think about the image or maybe your query, to process that by the engine, it's in the end gets converted to the vector, which you often refer as embedding for a lot of processing. Now, how does that magic happen? Well, the magic happens because those systems get very, very complicated. Like akin to a human brain, which is actually has you know, neurons, which are pretty simple things, but because we have so many of them, they can do amazing stuff. When we speak about large language models, we don't talk about the neurons, but what we talk about is a number of parameters, weights and biases, right? And if you look at the modern systems, they are dealing with trillions of them. Now, when we speak about the vectors, the very important concept here is a vector similarity. Now, to explain that, you can think about one of the well understood vectors in a space. I think you guys probably know what if you look at any color, it actually can be broken down to three different components: red, green, and blue, right? And so presented as a vector. And so two different colors can be seen as two different vectors. Now, think about though here, what makes colors different or similar? Well, that is something which you can decide upon, right? For your applications, it's more important to see the actual color, right? For example, the orange, wherever it's kind of very bright orange or dull orange is still a color for you. At the same time, if you're speaking about the colorblind person, for them, intensity of a color is much more important, right? And so the colors of the same intensity would look more of the same. The same things here. When we look about a vector similarity, we can use different concepts, and they could be different distances. Cosine similarity, Euclidean distance, and dot products are the most commonly used one. Now, while this is all theory, in practice, we can see the cosine similarity is the most commonly used way to compare vectors, and that is something which OpenAI recommends. Now, when we talk about the data processing, there are actually two kinds of vectors we may work with, right? And two ways to deal with information. One way is the sparse vectors, which are used in a lot of applications. And what they can correspond with is, let's say we have a word for, we have a large dictionary, and for every word in our dictionary, we would have a space and a vector. So when we process text, we can put the number for how many um, times their word was met in this text, right? Even as an actual number, or maybe as a, as a frequency, right? And then we can do a lot of text processing and for example, search applications with this kind. Like I would say, a lot of classical full text search algorithms were written with this in mind. The other kind of vectors, and this is the vectors which we use with embeddings, for example, is the dense vectors. Within the dense vectors we actually have all the dimensions in a vector contain values, and typically floating point values. They often have a lower dimensionality, even though still high. Now, how are those embeddings computed? Well, in this case, there is no specific rule like saying, oh, this dimension corresponds to color and this dimension corresponds to size or something like that. Well, we don't really know, right? It's just the model decides that. Here is an interesting example, which Jay Alamar's done. He had a model trained on a Wikipedia database, and then had like this relatively short, like small dimension presentation, right? And for different words, right? And the color in this case, well, that corresponds to their actual floating point number, which was in this case. And we can see in this regard, like, well, we may guess something, right? What's meaning of those things, right? But not quite, right? You can say, well, there is certain similarity between girl and a woman, but there's also differences, right? So I think that is a very important understand. What with embedding, we don't really try to reason about embedding in terms of what exactly every single dimension in embedding mean, right? It is just the properties of AI model which creates them, right? And we know what AI model creates the embeddings in a way what a similar concept, similar items would have the embeddings which are close to each other when compared as vectors. There is no right answer, right? And then also for different models, even different configuration used, you may have embedding which are completely different, right? And you have to keep in mind about that, right? When a database standpoint, when you change the models, you may need to regenerate your embeddings. And I think that it can be, tough mentality change, right? Because it makes it kind of hard to troubleshoot embedding generation when you don't quite know what the right thing is. Now, if you think about the vector similarity, vector databases, a vector similarity search, so actually finding the vectors which are close each other by distance, that is a core function. And that is different compared to your normal relational databases. Because if you think of classical relational databases, everything what we do is really based on this kind of similar concept of scalar comparison of value, more or less equals, right? And a B-tree, which optimizes that particular operations very, very well, right? The same thing happens with a vector search, but now we just need to deal with similarity or distance between the and computing the distance between vectors. And that's kind of similar to the other cases we had, like when full text search applications needed to be built or GIS applications. We all required additional functionality, additional index types in the databases, and so on and so forth. Now, if you think about relational databases, right? Let me explain the problem maybe in more details. If you think about embeddings, it actually is very easy to stack them as any data in something like blob or array type. And then you can use full table scan for search, right? And, compare all the elements and, compute the vector distances and, you can really perform the operation. The problem, though, it will be terribly, terribly slow because the classical B-tree index, hash index, right, or other kind of indexes your database may support, we're not really able to optimize this operation as well. To deal with this, you need some kind of different index. HNSW index, for example, is a very popular, though there are some other as well. KD indexes, ANOI, and so on and so forth. And there is a lot of development still trying to build algorithms which are able to provide this operation, the operation better, faster, and so on and so forth. There is also one more key difference between our classical database queries and B-tree indexes and the vector search. Vector search operations is not designed to be exact, right? We allow us some room for errors, right? As long as we are going to get approximately correct results, it's fine. And that is, I think, quite expected in a lot of AI and LLM applications, right? A lot of that is probabilistic as well. If you ask LLM the same question, a couple of times, you're not going to get exactly the same answer. It's going to be different. While if you think about the classical SQL, you are exact the same query on the same data, provide you the same result. Well, in majority of cases, right? Unless you are running explicitly non-deterministic query. Now let's talk about vectors in one particular database. In Postgres, because I think that is a truly the leader when it comes to the open source databases, and especially when it comes to enabling AI apps. I think the PostgreSQL is interesting in this case because you can think about three different levels of AI support in Postgres. On one extent, we have a PG vector, which is extension which enables us a core vector search when there is a PG vectorize, which provides some more features like interfacing of LLMs. And then there is also PostgreSQL ML, which gives you kind of even more kind of complete platform for building AI application, which based on Postgres, but which has another bells and whistles. What is also interesting is in the PostgreSQL space, when it comes to vector search, it's not just PG vector. I think this is awesome what PostgreSQL has such a great extension support, so we can have other extensions as well, right? We have a vector cord, which is an extension which claims to be, for faster and better than PG vector in a number of cases. There was also PG embedding application built by Neon, but then later it became archived if it features integrated in PG vector as, those proven to be useful. Here is example I wanted to show you about how you can use PG vector for what is called KNN. That stands for finding K nearest neighbors, like or closest vectors. In this example, we're using a very short dimensionality, right? It's a vector of just four dimensions, right? We can build an index on it, and they have a couple of objects, yellow bag and white bag, right? We have with with embeddings computed by some sort of model which we are not showing here. And then we can see another vector, right, which we computed for some other input, and we can supply the query and see what the distance for that thing is much closer to yellow bag compared to white bag. Maybe that was another yellow bag or something like that. PostgreSQL, though, is not the only choice. I think it's very interesting to see how much work MariaDB put into building the vector search functionality. And according to some benchmarks they publish, it actually has a pretty good performance, right? I specifically want to quote here Mark Callaghan, who is somebody who's a very respected open source database performance expert, right? And he has done some benchmarks, and so I believe those are correct. So that's really very interesting to see some competition here, and probably those communities learning from each other. Let me touch on quickly, though, about how vector search benchmarks work. As I mentioned, the vector search operations are not expected to be exact, right? So when we are looking at performance, we are also looking at the performance of a given recall rate. And recall, that is specifies as how correct results are, right? So when we speak about the recall of 95%, for example, then that means what the 95% of results in the result set actually match your query. And another 5% could be, some garbage, right? There are some other complexity though, right? Like, for example, some of the algorithms, some of the data structures to enable vector search, they can be very good for search speed, but can be very expensive to update, right? So in this case, you also need to understand, well, what is expectation? Is it expansions, what we are doing in benchmarks, an immutable database, slowly changing database, or constantly changing content, right, which can change? What is also interesting in this case is the most commonly used index type, HNSW, has configuration parameters. And those configuration parameters are kind of hard to reason about, right? So it's hard for people to tune, and I think that is somewhere where we're going to see some improvements in a due time, because usability is important. So semantic search. Semantic search is something which I think is awesome, and that can be implemented through a vector search. It can replace a lot of classical manual solutions, right? If you look about search engines, a lot of work have been used in dealing with synonyms, morphology, misspellings, and so on and so forth, which vector search with some good AI models just deals automatically. Additionally, it can support multi-languages and multi-models, right? It's can automatically, return you images, right, as we showed. Here is a couple of examples I wanted to show you from our friends in Manticore. One is this GitHub search, which is very interesting because we are searching for memory leak here, but you can see there are a bunch of queries, a bunch of responses here, which actually have no memory leak keywords, but they are actually about some problems with memory. And here's another one. right? We're speaking about the multimodality, right? We used some multimodal model here called TinyClip, and we can see in this case looking for entering a text query for formal shoes or running shoes, right? We can actually get results from collection of images, right? I think this is pretty awesome. And again, for both those examples, you can check out the source on the GitHub using the QR code provided here. Now, there are some disadvantages here, though, too, with semantic search or KNN-based search. It's kind of higher computation costs. It's also less explainable, right? If you're getting some results for this kind of search, it's harder to debug that compared to while your full text search gives you something. And it's also not exact. If you can say, well, I want all documents which match exactly this phrase, and no documents which don't have this phrase, it's hard to implement with a vector search, right? Because of the data structures what we use. One approach, what can be also used, is a hybrid search. With hybrid search, and it's actually known to give you the better results at the lower computational costs. And the idea here could be, for example, we are using full text search, right, to pull up the documents, and then we are using some sort of vector search, right, to rank those results or process them. There also vector search can be used is RAG, Retrieval Augmented Generation. And this is something which is a very important use case, right? Especially for enterprise use cases. Many companies have a lot of data, right? Which they want to work with LLMs with, but they don't particularly want to upload that to any public model, right? So what can work in this case is what you can have the LLM, which kind of have a lot of smarts in general language understanding, right? Where it can work together with your data in your organization without exposing that into the public, right? By providing you relevant answers. For example, you may have a knowledge base, right? And then you have somebody gets a query that gets processed with knowledge base, and then the article or articles matching from a knowledge base together with a general LLM knowledge can be used together to provide the answer. And similarity search is used, as you can see from the diagram, as a part of that. Finally, I wanted to touch on some interesting developments which I think are going on right now. One is there is a lot of work on improving quantization. So what is quantization? Is really simplifying our vectors, right? So instead of using 32-bit floats, maybe we are using 8 bits per value, or even maybe 1 bit, right? And it is possible to do that, compressing significantly data set without losing quality that much, right? And that is, I think, one of the ideas how we can get better model running on a smaller hardware. Like, for example, it's now possible to with quantization to run the DeepSeek models. That's relatively a commodity server, which can be cost just a couple of thousand of dollars. Another, I think, interesting idea is to replace RAG with a large context. The idea there is if your database is kind of small enough, the knowledge, the enterprise knowledge you want to work with, you just may supply that into the context window, right? Kind of that sort of like a chat history, if you will, and work with that instead of RAG. In certain cases, that provides us with better results. Well, with that, we came to the end of my presentation. And let me repeat some of the things as a conclusion. Obviously, their supporting AI applications is going to be a key feature for key feature for a database in the future, right? And a lot of that is going to be based on vector search, right? We'll have a databases getting better and better to really support developers building AI applications, as well as AI agents, which will increasingly participate in the application creations, right? I think we'll continue having the general purpose databases getting better and better at AI, as well as the specific AI vector search databases, right, the, being used for some very advanced use cases. I also expect a lot of work continue to be done in performance, efficiency, and ease of use, as happened with pretty much any other database feature in the market. And with that, I am sure when we'll meet again for this conference, we'll have some new awesome stuff to talk about. Thank you.